Okay, let's get into this. When you think about Antarctica, you probably picture, this vast white frozen emptiness.
Right, a continent of ice.
Exactly. But there's a specific part of it, a huge body of water called the Weddell Sea, that somehow manages to hold two completely contradictory world titles.
Yeah, they really are polar opposites.
On the one hand, it has the clearest water ever measured. I mean, we're talking clearer than a mountain lake, almost like distilled water.
And on the other hand,
On the other hand, historically, it's known as the most treacherous, most dismal region on Earth. It was, for a long time, the place where explorers went to die.
and that paradox, that stunning clarity paired with the most extreme danger is exactly why the Weddell Sea is such a fascinating and critical place for us to dive into today.
So this isn't just a big bay we're talking about.
Or not at all. It's a foundational piece of the entire Southern Ocean.
Yeah.
Geographically speaking, you're looking at a massive bay that's bounded by Coates Land on one side and then the curving sweep of the Antarctic Peninsula on the other.
And when we say colossal, we really do mean it. This is not some minor inlet.
No, absolutely not. We're covering an area of about 2.8 million square kilometers.
Wow!
To give you some perspective on that, it's larger than Greenland.
That's incredible.
So yeah, it's this vast, incredibly influential basin, and its unique position, its remoteness, is precisely why it plays such a huge and often hidden role in regulating the entire global climate system.
So if you want to understand the planet's deep ocean currents,
You have to understand the Weddell Sea. It starts there.
so for you, our listener, our mission today is to go way beyond just the map coordinates. We are going to trace the history of disaster and survival, especially the haunting story of Ernest Shackleton and his ship, the Endurance.
And then we'll get into the science, the really cutting-edge stuff.
Yes, exploring that deep water formation process that, and this is no exaggeration, effectively keeps the planet's entire ocean conveyor belt moving.
And then we'll finish by looking at this hidden ecology that's just, well, it's redefining what complex life can even look like in the deepest, coldest, and darkest parts of the Antarctic.
Some of these discoveries are genuinely mind-bending.
They are. But before we jump right into the physics of it all, there's a quick but a crucial note on geography we should make.
Oh.
This region isn't just defined by ice and water. It's also defined by competing claims. The Weddell Sea sits right within these overlapping Antarctic territorial claims.
So you have multiple countries laying claim to this same patch of ocean.
Exactly. The area is claimed by Argentine Antarctica, the British Antarctic Territory, and then it's also partially claimed by the Antarctic Chilean Territory.
And why does that matter for a deep dive like this? I mean, from a scientific perspective.
Well, it adds all these layers of complexity, It affects who can research where and under what flag they're doing it. So when you see these huge expeditions, like the ones that found the Endurance or discovered that icefish megacolony we'll talk about, they are almost always multinational collaborations.
Because they have to be.
They have to be. Now, the treaty system means that all those claims are, in theory, suspended. But in practice, national interests are still guiding logistical support, how resources get allocated, and, this is the crucial part, the long-term monitoring of things like ice shelf health and deep water warming.
So understanding the governance helps explain why it might be so hard to get a big, coordinated project off the ground.
Precisely. It's a scientific frontier, but it's also a geopolitical one.
All right, let's start with the physical reality of the Weddell Sea, because it is just an environment of profound extremes. This isn't just an empty patch of ocean. It's bounded and defined and fundamentally governed by ice, a lot of which is permanent.
That's absolutely the key distinction here. If you look at the physical boundaries, the eastern limit is marked by a place called Cape Norvegia, which is on the Princess Martha Coast in Queen Maud Land. And to the east of that cape, you have the King Haakon the Seventh Sea. But the structure that really truly dominates, especially the whole southern part of the Weddell Sea, is the massive, permanent Filchneron ice shelf.
An ice shelf, so that's not sea ice, that's glacial ice floating on the ocean.
Exactly. These are gigantic floating tongues of glaciers that have flowed off the continent, and they fringe almost the entire southern rim of the sea.
And these shelves, even though they're enormous, are also the most dynamic and, I guess, vulnerable parts of this environment, aren't they?
They are. They're like the planet's canaries in a coal mine. They are incredibly volatile indicators of climate stress.
And the sources for this dive mention some pretty dramatic changes.
Yes, the dynamics have been visibly, shockingly dramatic in recent decades. Specifically, Certain ice shelves along the east side of the Antarctic Peninsula, which used to cover something like 10,000 square kilometers of the sea's surface, had completely disintegrated by 2002.
Wait, 10,000 square kilometers? That's a huge area of ice structure to just disappear.
It's massive. Gone in a very short period, geologically speaking.
What does that do locally when you lose that much floating ice? What are the consequences?
Well, the immediate local effect is you suddenly have these large areas of open water where there used to be bright white ice. That dramatically changes the reflectivity, the albedo, so the ocean absorbs more solar energy.
And it heats up.
It heats up. But maybe more importantly for the whole planet, these ice shelves act as buttresses. They're like a cork in a bottle, physically holding back the massive land-based glaciers behind them.
So when the shelf goes,
The inland glaciers speed up their flow into the ocean, and that contributes directly to global sea level rise. Now, the Filson-Around ice shelf itself is still vast, but the losses along the peninsula, they signal this profound instability in the whole local marine environment.
okay, so let's shift from that dynamic, treacherous ice to the stillness and the purity of the water itself. This is where we get to the Weddell Sea's record-setting clarity. I just have a hard time wrapping my mind around how a sea surrounded by constantly melting, grinding ice can also be the clearest water on Earth.
It is astonishing. And the finding, it comes from this really rigorous oceanographic research that was done by the Alfred Wegener Institute way back in 1986.
And how did they even measure that?
They use one of the simplest, oldest scientific tools in the book, the Secchi disk.
For anyone who doesn't know, could you remind us what a Secchi disk actually is?
Of course. It's literally just a circular disk. Traditionally, it's about 30 centimeters in diameter, and it's painted in these alternating black and white quadrants.
And you just lower it into the water.
You lower it into the water, and the depth at which the observer on the ship loses sight of it, that measures the water's transparency. It's an old method, but it's incredibly effective for measuring suspended particles in the water.
So in most oceans, you might see it for, what, 20 or 30 meters?
If you're lucky. In many coastal areas,
Yeah.
much, much less.
So what was the number they recorded in the Weddell Sea?
The disk was visible at an astonishing depth of 80 meters. 80 meters.
Yeah.
That's 260 feet.
I'm trying to picture that. That's like standing on top of a 26-story building and being able to clearly see a pizza box on the sidewalk below.
That's a great analogy. That level of transparency is it's virtually unheard of in any natural body of water on the planet.
And what's the big scientific takeaway from a reading like that? What's the implication?
The scientists who made that measurement, they correlated that extreme clarity to the purity of distilled water.
Wow.
The implication is that there is a near total absence of suspended material in the water column. So that means two things. First, very little silt or sediment is getting into the water, probably because it's being trapped by those massive ice shelves.
And the second thing?
Second, and this is critical, it means there are extraordinarily low concentrations of phytoplankton.
The microscopic plant life that forms the base of the food chain.
Exactly. The very stuff that typically makes ocean water a bit cloudy or green.
So that connects directly to the ecology we're going to talk about later. If the water is that clear because there's no phytoplankton, it means the foundational food source for the entire marine ecosystem is incredibly scarce, at least in that surface layer.
Precisely. It creates this highly specialized, nutrient-poor, yet light-rich environment in that upper layer, which is a sharp contrast to the productive, plankton-dense waters you find almost everywhere else.
So you have this pristine, almost sterile water, yet historically it's feared more than any other sea on the planet. Let's dig into that fearsome reputation. How did it get the name most treacherous?
That dread is it's so deeply rooted in the experiences of the first explorers. There's a book from 1950, The White Continent by Thomas R. Henry, and he really codified the sea's terrifying reputation. He set it apart from all other Antarctic regions.
What did he say specifically that captured this dread so well?
He wrote it, I'm quoting here, that the Weddell Sea is the most treacherous and dismal region on Earth.
That's a strong statement.
A very strong statement, and he contrasted it directly with the other side of the continent, specifically noting that the Ross Sea was, in his words, relatively peaceful, predictable, and safe.
So, if it wasn't always about having the thickest ice, what made the treachery here so unique?
Henry pointed out that it wasn't just the sheer volume of ice, but the nature of how it formed and moved. He wrote about these treacherous flash freezes.
Flash freezes?
Yeah, where the sea could just freeze over rapidly, unexpectedly, trapping ships almost instantly and embedding them in the pack ice. This extreme speed and total unpredictability made any kind of navigation a nightmare. He actually noted that ships couldn't reliably find a path to the coast until as late as 1949.
And you mentioned an anecdote, sort of a myth, that really gets at the psychological toll of this place.
Yes, and this is just to underscore how alien and fearsome this place felt to those early sailors. Henry passed on an account of a mythical sighting of a green-haired merman in the icy waters. A green-haired merman. It sounds completely absurd to us today, but it speaks volumes about the sheer terror and the psychological strain that must have just blended reality and hallucination for explorers who were stranded in this profoundly isolated, dangerous, and unpredictable place.
The green-haired merman is definitely a detail that sticks with you. So to round out the geography before we get into the exploration history, the sources mention all these seabed features, banks, knolls, troughs. Why are those important?
They are absolutely critical for understanding the deep sea physics, which is what we'll get into in Section 4. The sources list features like, Albert Bank, Bem Bank, Hoffman Trough. These bumps and valleys on the seabed, they're like the plumbing of the system.
They steer the water.
They steer the water. They dictate exactly where that dense, sinking water, the global engine we're going to talk about, is channeled.
Yeah.
They can create bottlenecks or guide the currents, and that directly influences the speed and the direction of the deep ocean masses that eventually flow out of the Antarctic to the rest of the world. #3, a history of peril and discovery.
The physical environment of the Weddell Sea has made it the stage for some of the most dramatic stories in Antarctic exploration. Stories of survival, tragedy. Its very name carries so much historical weight.
It really does. The sea was named in 1900, but not by its discoverer. It was named in honor of a Scottish sailor, James Weddell.
And he found it much earlier than that.
Much earlier. He discovered it back in 1823, though at the time he originally called it the King George V Sea, after the ruling monarch.
And when Weddell made that discovery, he managed to get pretty far south, didn't he?
He was remarkably successful for that era. He reached a latitude of 74 degrees south, which was a major achievement.
But there was another claim around that time, wasn't there?
There was. In that same year, an American sealing captain named Benjamin Morrell claimed he'd discovered a place he called New South Greenland, which he placed about 10 or 12 degrees east of the sea's actual boundary.
And that turned out to be not real.
It was later disproved when the area was more thoroughly explored. Morrell's claims sort of highlight the navigational uncertainty and sometimes the outright fabrication that marked some of those early ventures. But it also just underscores how difficult it was to accurately map and penetrate this specific region.
So after Weddell, who pushed the boundary further?
The furthest south penetration before we get to the modern era was achieved by a man named William Spears Bruce in 1903. Every single degree you gained heading south was a brutal, hard-won battle against the ice.
And speaking of brutal battles, that brings us to the early 20th century and the disastrous but also heroic Nordenskjöld expedition.
Ah, yes, between 1902 and 1903. That story really highlights the volatile nature of the ice right around the Antarctic Peninsula.
The leader was Otto Nordenskjöld.
Right, he led the Swedish Antarctic expedition, and the hostile conditions they faced are sort of memorialized in the geography itself. His expedition ship, the Antarctic, gave its name to the Antarctic Sound.
Which is the channel that separates the tip of the peninsula from Dundee Island.
That's the one. And it has a very chilling nickname.
Iceberg Alley.
Iceberg Alley. It is notorious for the sheer concentration of massive icebergs that calve off the glaciers and ice shelves there. It makes passage exceptionally dangerous, even for modern icebreakers.
And for Nordenskjöld's wooden ship, it was fatal.
It was. The conditions proved lethal. The ship was crushed by the ice and sank in 1903.
And that event triggered this incredible multi-year survival ordeal for the crew who were split into different parties. It's hard to imagine today.
It was a supreme test of endurance. Nordenskjöld himself and 3 of his men were forced to spend 2 brutal, completely isolated winters, 2 full years, in a makeshift cabin they built on a place called Snow Hill Island.
2 winters.
2 Antarctic winters. They survived on the absolute minimum of supplies, constantly battling the cold, the darkness, the sheer mental strain of total isolation. The fact that they survived is a stunning testament to human tenacity, but it also just screams volumes about the unforgiving nature of the environment that trapped them.
But the story that truly defines the Weddell Sea's treachery is the one that was a catastrophic failure that somehow became the ultimate survival story.
Shackleton and the Endurance.
Shackleton and the Endurance.
The 1915 disaster is the definitive illustration of the Weddell Sea's power. Shackleton's Imperial Transantarctic Expedition was aiming to be the first to cross the continent on foot.
But they never even made it to land.
They never even set foot on the continent proper. Their ship, the Endurance, became trapped in that rapidly closing pack ice we talked about.
So those flash freezes that the writer Henry mentioned.
That phenomenon was their undoing. The ice just closed in, pressing on the hull for months, until the ship was eventually crushed and sank beneath the ice.
And what followed for the crew is just legendary.
It is. They spent 15 months living on the pack ice itself, a constantly shifting, cracking, moving platform of ice, drifting north at the mercy of the Weddell Gyre and the winds.
That journey, just the transition from being on a ship to being on the ice, and then finally getting to Elephant Island in lifeboats, and Shackleton's own journey for rescue. It's one of the greatest feats of survival ever recorded.
It's an absolute miracle they all survived. But the story has this remarkable modern postscript that tells us even more about the Weddell Sea itself.
The discovery of the wreck.
Exactly. In March of 2022, the wreck of the Endurance was finally discovered.
And the condition it was in was shocking, right?
It was reportedly in a state of remarkable preservation, almost frozen in time at a depth of 3,008 meters.
That's nearly 10,000 feet down.
Yes. The environment down there, intensely cold, deep, and very low in oxygen, acted as a perfect preservative. You can still read the name Endurance on the stern.
But the location of the wreck, it wasn't exactly where they thought it would be.
No, it was found 4 miles away from where the historical records predicted it sank.
And that 4-mile discrepancy tells us something fundamental about the physics of the sea, doesn't it?
It really does. It highlights the extreme chaotic nature of the ice flows that were carrying them. 4 miles is a big difference. The ice where the Endurance sank was not a static block. It was this turbulent, dynamic environment of constantly moving, sharing flows, all dictated by those powerful surface winds and the underlying currents.
So that small difference in the wreck site confirms just how relentless and unpredictable the whole region is, even with our modern technology.
It's a frozen monument to the sea's power to destroy and then, paradoxically, to preserve.
Okay, so we've covered the deadly history, the geographic extremes, from that 80-meter water clarity to the constant crush of the ice. But the reason the Weddell Sea truly matters on a global scale, the reason everyone, everywhere, should care about this remote body of water, is found deep below the surface.
Right. Not in the surface dramas, but in the specific physics of its deep water.
It is, and this isn't an exaggeration, one of the world's most critical climate engines.
It is a fundamental global driver, yes. And to really understand this engine, it helps to quickly connect its modern oceanography back to its deep geological roots. It actually have a shared ancient history with the southern tip of South America.
How does an Antarctic sea connect geologically to Patagonia?
Well, the formation of the Weddell Sea is a story of tectonic plates moving apart. It's tied to what's called extensional tectonics back in the Jurassic period. This process created something called the Rocas Verdes Basin, which was essentially a back-arc basin that stretched between the two landmasses before they fully separated.
So the Weddell Sea is what's left of that ancient basin.
It's the surviving extension of it, yes.
So they were once connected, but their paths diverged pretty dramatically.
Precisely. Later on, in the late Cretaceous and Cenozoic eras, the South American part of that basin got squeezed. It was subjected to intense compressional tectonics, and it buckled and folded into what we now know as the Magellanic Basin.
But the Weddell Sea part didn't get squeezed.
It escaped that compression. It stayed relatively stable, and it preserved its structure as a deep oceanic basin. And that geological foundation, this deep, stable, relatively uniform basin, is the necessary prerequisite for the massive, continuous oceanographic processes that we see happening there today.
Okay, so let's get to those processes. Deep water formation. This is where the physics of the Weddell Sea directly impacts, well, billions of people. It governs the global thermohaline circulation. How significant is the Weddell Sea in that context?
Its role is, it's possibly irreplaceable. The Weddell Sea is one of only a tiny handful of locations on the entire planet where deep and bottom water masses are formed at scale.
And these sinking masses of water are what drive the whole system.
They're the motors. They drive the global thermohaline circulation, which people often call the global conveyor belt. And that belt is responsible for distributing heat, storing carbon, carrying oxygen, and moving nutrients all across the world's oceans over thousands of years.
That is a huge amount of responsibility for one remote sea. So walk us through it step by step. How does the water get dense enough to kick off this planet-wide conveyor?
The main mechanism involves two processes that are coupled together: brine exclusion and wind cooling. Together, they facilitate something oceanographers sometimes call cabling.
Cabling.
It's a term for when water masses mix and then sink because their combined density increases. So first, you have brine exclusion. As the intense Antarctic cold forces new sea ice to form really rapidly on the surface, the salt gets rejected.
So the ice itself is freshwater.
The ice is fresh water, but the brine, this super concentrated salt solution, is pushed out into the remaining liquid water underneath.
Which makes that water incredibly salty and therefore heavier.
Exactly. It massively increases the water's salinity and thus its density. At the same time, you have these intense, dry, cold Antarctic winds that are just constantly battering the surface, cooling that newly salty water down dramatically.
So it's getting saltier and colder at the same time.
The perfect combination. It creates this exceptionally cold, dense water mass that is now significantly heavier than all the water surrounding it.
And gravity takes over.
Gravity takes over. It sinks, it cascades off the continental shelf break, and just descends into the abyss. And this forms the Weddell deep water and the Weddell bottom water masses.
Which then flow out and power the conveyor belt.
They flow northward, spreading their cold, dense characteristics throughout the world's deep oceans, literally powering the whole system.
It sounds like a really stable perpetual engine. But you mentioned earlier that it's showing signs of stress. What is the latest research saying about its current state?
Well, the process is incredibly sensitive to global changes. The sources we're looking at highlight that scientists have measured multi-decadal warming and, crucially, a loss of density in the deep water masses of the Weddell Sea just over the last decade.
Density loss. How is that even measured, and what does a tiny change actually mean for the conveyor belt?
Well, density is highly sensitive to both temperature and salinity. A shift of even a few hundredths of a degree Celsius can be hugely significant when you're talking about these vast volumes of water.
So what's causing the density to drop?
It could be a couple of things. If the surface water gets a little warmer, or if increased glacial melt from the continent adds too much fresh, less dense water into the mix, the whole sinking process can slow down or weaken.
And if that continues?
If the density loss continues, the water masses don't sink as effectively. You could end up with a stratification, a layering of the deep ocean. This, in turn, weakens the conveyor belt, which reduces the transport of heat north and, just as importantly, reduces the supply of oxygen and nutrients to the deep sea.
So the stability of the entire global ocean is balanced on the physics of salt being pushed out of ice in this one remote sea. That's a powerful thought.
It really is.
So once that dense water is formed, how does it get circulated out? It's governed by a massive rotation, right? The Weddell Gyre.
The Weddell Gyre, yes. It's this immense circulation pattern that organizes all the water within the sea. It's cyclonic, which means it rotates clockwise in the southern hemisphere, and it's primarily driven by the wind, although that underlying flow of dense water heavily influences its deeper structure.
And what's the gyre's ultimate job in this global movement?
It's both the internal machinery and the final exit ramp. The gyre has this northward flowing current along its western boundary, right up against the Antarctic Peninsula. That current is the primary way that these water masses, including the Weddell deep water, leave the sea and enter the wider world ocean.
And it mixes into the South Atlantic from there?
Exactly.
You mentioned it has a complex vertical structure. So what does an ocean sandwich look like in the Weddell Sea?
It's a very specific layered stack. At the very top, you have a cold, low salinity surface layer, which is heavily influenced by melting ice.
Okay.
That's separated from the layers below by a pretty thin layer called a pycnocline.
And a pycnocline is what exactly?
It's the layer where the water density changes very rapidly with depth, so it's a major transition zone. And beneath that pycnocline, you have this thick, crucial layer known as Weddell deep water, or WDW.
Now, the WDW is often described as relatively warm and salty. How can water that's thousands of feet deep in the Antarctic be considered warm?
It's the paradox of salinity. The WDW is relatively warm. We're talking maybe a degree or two above freezing, but that's compared to the frigid surface water and the even colder bottom water.
And where does this warm water come from?
It actually originates from warmer, saltier, deep water masses that circulate southward towards Antarctica from other oceans. Because it's so salty, it's still very dense enough to sit beneath the colder surface layer, which, despite being colder, is much fresher, less salty, and therefore less dense.
And below the WDW?
Below the WDW, you finally have the really cold, really dense, newly formed Weddell bottom water, the stuff that just sank.
Given how important the gyre is, you'd think quantifying its circulation would be a top priority. Has that been easy to do?
Quite the opposite. It's been historically very, very difficult to quantify. Early data, things like geopotential surface height measurements, they only indicated very weak surface currents.
Which was misleading.
Very misleading. Because we know the Weddell Sea is this massive source of dense, sinking water. Researchers have always expected there to be a much stronger, deeper circulation along that western boundary, driven by the continuous input of all that heavy water from the south.
So weak currents at the top are masking a powerful, deep river of water below.
That's the idea. The available historical data just hasn't really allowed for an accurate quantification of the volume transports. How much water is moving and how fast in that deeper density-driven flow. Modern oceanographic tools are constantly trying to capture that number because knowing the exact output of the engine is vital for all our climate models.
Okay, let's shift back to the surface drivers, the winds. Wind cooling is key to the deep water formation. But the meteorology of the western Weddell Sea is really unique, isn't it? It's channeled by the geography of the Antarctic Peninsula.
It is a remarkable atmospheric interaction. A defining feature of the western Weddell Sea climate is the dominance of these exceptionally strong surface winds that run precisely parallel to the spine of the Antarctic Peninsula.
And the peninsula is a very tall, narrow mountain range.
Exactly. The winds are channeled and intensified by the topography itself.
What direction do they move, and what effects do they have?
They carry intensely cold air from the continent towards the lower latitudes, and they eventually turn into southwesterlies as they move farther north. But crucially, this persistent flow acts as a continuous conveyor belt for ice. It forces all the pack ice and the smaller icebergs northeastward, out into the South Atlantic.
So the wind isn't just cooling the water, it's physically exporting ice out of the sea.
Constantly. And this is what creates that long-known razor-sharp contrast between the conditions on the two sides of the Antarctic Peninsula. The eastern Weddell side is perpetually harsh and ice-choked, while the western side can be comparatively milder and more open.
That process of cold air piling up sounds incredibly complex. Can you walk us through the meteorological mechanism that creates these powerful channeled winds?
Certainly. These strong northward winds along the east side of the peninsula are usually generated by one of two large-scale weather systems. The first and simpler one is an intense low-pressure system, a cyclone, that forms out over the central Weddell Sea, and that just pulls the air masses toward it.
And the second scenario?
The second, and I think more interesting situation, involves a broad, stable flow of cold, dense air moving from east to west in the lowest part of the atmosphere, say the lowest 500 to 1,000 meters. And it's directed right at the Antarctic Peninsula.
And the mountains act as a solid wall.
A complete barrier. When this stable cold air hits that narrow, tall mountain range, it can't easily flow over it. So instead, the air begins to pile up against the eastern edge of the range.
A traffic jam of cold air.
A perfect description. This process of cold air piling up creates a persistent high-pressure ridge, which is focused mainly over the eastern peaks of the mountains. And that ridge then deflects the incoming air current sharply to the right, thanks to the Coriolis effect in the southern hemisphere.
So instead of crashing into the mountains, the wind is forced to just rush along the mountain wall, creating this continuous, intense flow.
Exactly. It's like turning a fire hose down a narrow channel. The mountains convert a general flow of cold air into a high-velocity channeled wind that defines the climate of the western Weddell Sea. It's a perfect, relentless, cold wind machine, constantly driving that brine exclusion process that the deepwater engine needs to run. Hashtag VV. The surprisingly rich ecology.
The great irony of the Weddell Sea is that this environment, which we've defined by its lethality, its constant churning ice, and its almost distilled water clarity suggesting a food desert.
Right, suggesting there's nothing to eat?
Is in reality home to some of the most vast, complex, and frankly rule-breaking ecosystems on the entire planet.
That juxtaposition is truly amazing. Even at the surface, the sea supports a lot of characteristic fauna. You have the whale seal, which is named for the sea itself, along with killer whales, humpback whales, minke whales, leopard seals, and crab-eater seals.
So despite the difficult ice, these large mammals are thriving.
They are. They thrive on the upwelling and the local concentrations of food that happen, even in that harsh environment.
And of course, the most iconic residents, the penguins.
But the Adelie penguin is really the dominant species here. It's highly adapted to that harsh, high-latitude environment. We see these immense nesting grounds, most notably a massive colony of over 100,000 breeding pairs of Adelies. and that's centered on a place called volcanic Paulet Island.
And there was also the discovery of an emperor penguin colony, the northernmost one, which connects back to that theme of treacherous navigation.
Yes, that's a great point. Around 1997, scientists discovered the northernmost known colony of emperor penguins, just south of Snow Hill Island.
Which was a surprise because they're typically found much further south.
It was a big surprise. But just accessing that colony emphasizes the sea's inherent difficulty. To get there, you need a powerful ice-class research vessel, and it has to be specifically equipped with helicopters.
Why the helicopters?
Because the persistent, heavy, and unpredictable pack ice often makes surface navigation completely impossible, even for the best icebreakers. You have to fly in over it.
Okay, now let's get to the real rule breakers. Life that is thriving, where science previously said it absolutely could not. Let's start with the discovery under the permanent ice shelf. It fundamentally challenges our understanding of biological energy and survival.
This 2021 finding is still sending shockwaves through the biological community. Scientists reported finding sessile organisms, so things like sponges and other unidentified suspension feeders that filter food from the water,
And they found them growing on a boulder.
under the vast Filchneron ice shelf.
Let's nail down the specifics of the location because the numbers are just unbelievable.
They are. The depth of the discovery was 12,233 meters down, and of that, 872 meters was solid, permanent ice above them.
Okay, so nearly a kilometer of ice.
And then, the critical distance. They were located a staggering 260 kilometers. That's over 160 miles from the nearest open water.
From the nearest possible source of sunlight or surface-level nutrients.
Exactly.
But sponges are filter feeders. They need food particles sinking down through the water to eat. How on earth does food travel 260 kilometers sideways underneath hundreds of meters of permanent ice?
That is the $60 million question. This discovery just completely shattered the conventional limits for where a sessile, benthic community, so a fixed, bottom-dwelling community, can survive.
So what are the theories? How could they be surviving there?
Scientists have proposed a few hypotheses, and none of them really fully explains the scale of what they found.
Okay.
One possibility is that the deep ocean currents, which are guided by those seabed features we talked about, are moving organic particles along the bottom very efficiently and over these vast distances. But the energy required to sustain a filtering community over 260 kilometers is just immense.
What's another idea?
Another hypothesis involves extremely low metabolic rates. These organisms might be growing incredibly slowly. They might only be consuming just enough food to survive for decades or even centuries, rather than thriving in a traditional sense. They could be ancient.
Could they be using some other food source, like chemosynthesis, something not based on photosynthesis at all?
That's a possibility too, though it's less likely for standard sponges. The particles they're filtering could be ancient, having sunk years or centuries ago, or they might be relying on some previously unmeasured geological or chemical input from the seabed itself.
So no matter what the answer is, the fact that they exist forces us to redraw the map of where life is possible.
Completely. It suggests these vast hidden ecosystems could exist anywhere.
Yeah.
You have a stable rock surface and even a minimal current flow, even in permanent darkness, miles under a permanent ice sheet.
That is truly profound. And speaking of vastness, that same year brought another discovery of life. Not isolated under the ice, but thriving on the seafloor in colossal numbers. The icefish megacolony.
This discovery, made by the same Alfred Wegener Institute with their research vessel RV Polarstern, was equally historic. They found a colony of approximately 60 million Jonah's icefish.
60 million?
60 million active nests. And these fish are instantly recognizable because they're one of the only vertebrates known to have transparent blood. They completely lack red hemoglobin.
Transparent blood, that's a stunning adaptation to the cold.
It's an incredible adaptation. In the extremely cold, oxygen-rich waters of the Antarctic, not having hemoglobin actually reduces the viscosity of the blood. It allows it to flow more freely and efficiently at temperatures near freezing, which is absolutely critical for survival in that deep, frigid abyss.
And 60 million fish in one area. That number is almost impossible to picture. What's the scale and the density of this breeding ground?
The colony is estimated to cover around 240 square kilometers of the seabed.
And the density?
To put that into perspective, scientists observed an average of one active nest for every 3 square meters across that entire immense area.
So this isn't just the largest fish breeding colony found in the Antarctic.
It's the largest known fish breeding colony discovered anywhere in the world, by far.
And what does that tell us about the deep Weddell Sea as a habitat?
It underscores that the abyssal conditions of the Weddell Sea, so cold, stable, and incredibly consistent over time, provide a perfect protected environment. It's a nursery for these very specific, cold-adapted species to organize and reproduce at a scale we simply don't see in more turbulent environments.
So the stability is the key, while the surface is a chaotic nightmare.
The deep Weddell seawater masses provide this remarkably consistent habitat, and that allows these slow-growing, highly specialized species like the icefish to establish these massive protected nurseries far from surface predators and chaos. It shows that the most treacherous sea is also, paradoxically, a cradle of life. #CCs. Conclusion and takeaway.
So we've wrapped up our journey through the Weddell Sea, and what a collection of contradictions it is. We started with that central paradox. The clearest water on Earth, yet at the same time, a deadly, ice-choked navigational nightmare that famously trapped Shackleton and his crew.
Then we trace its absolutely essential role as a global climate engine, a deep water factory that's powered by wind cooling and brine exclusion physics that dictate how heat is distributed and stored across all the world's oceans.
And then, most surprisingly, we found that beneath all that chaos and that strange clarity, this remote body of water harbors life in conditions we previously thought were impossible.
Filtration feeders surviving 260 kilometers under permanent ice.
And a 60 million strong colony of transparent blooded fish, all thriving in the frigid abyss.
So, if there is one single essential nugget of knowledge that you should take away from this deep dive, it is the fundamental global significance of its hydrophysics.
Its role in deep water formation.
Exactly. The Weddell Sea's contribution to deep water formation and the thermohaline circulation is absolutely, positively irreplaceable. The efficiency of that ocean engine determines the ventilation, the nutrient renewal, and the temperature stability of ocean basins all over the world.
So the stability and consistency of that process is paramount. The future of the global ocean climate is just. It's inextricably linked to the complex, density-driven physics happening in this one remote Antarctic region.
And this brings us to the final provocative thought for you to consider. We know that the deep sea ecology we just discussed, that 60 million strong icefish colony, the sponges 260 kilometers from open water, is completely reliant on the extremely cold, consistent, and stable conditions provided by that Weddell deep water. But as we mentioned, scientists are already measuring multi-decadal warming and density loss in those very same deep water masses. It's a potential sign that the engine is already struggling.
So if the fundamental, stable, cold water conditions that allow this unique, specialized deep-sea life to flourish begin to degrade because of climate change, what hidden specialized ecosystems, the ones currently dependent on the deep, cold, and consistent environment of the Weddell Sea, might be irrevocably altered or even lost entirely before we ever even manage to discover them and understand how they survive?
The clearest, deadliest sea isn't just a historical marvel. It is perhaps our most crucial and our most fragile planetary bellwether.